And there we go. Point that down. So everybody, you're on YouTube. If you don't want to be on YouTube, you can sit in a corner or something, or yeah. And here we go. So hi everybody. So I like to do introductions to start with. So this is Salt Lake City Python. Kind of told you about them. Utah Python is a group of all kinds of Python meetup groups around the state. Everything from Python Utah North, which is over here, looking at his screen. Hi, Python Utah North. Yeah, in Logan. That's also my pops. And let's see, we also provide resources for, oh yeah, that's what we do. This should be indented. See, this is why white space is important, am I right? And let's see, so we also have the PyLadies. They're actually having a meetup tonight, which I wasn't aware of, and I probably should have checked, but they planned it like 3 months ago, and I was like, well, we are always the first Wednesday, so I kind of feel bad that we're still having ours, but it's okay. They meet once every 3 or 4 months, and it's kind of been inconsistent, so it's kind of hard to schedule around them. We are almost always the first Wednesday of the month, the exception being if there's the 4th of July and it's right on the meetup time or right before or after, we try to move it. And then same with New Year's Eve, or sorry, New Year's and New Year's Eve. So when that happens, yeah, it'll never be New Year's Eve technically, but it could potentially be New Year's Day. So when that happens, we try to move it around. And I always make sure to inform everybody of that. Let's see, who else do we got? We have Python at the Point, which is based not out of Needle. I always write Needle, but they're at a different spot now. They're in, they are at Thanksgiving Point, so they are the ones for the people down south. There's also Girl Develop It, SLC. So, by the way, the PyLadies, men are more than welcome to join. They do have a woman focus, but men are more than welcome to join. Girl Develop It, SLC is more women-oriented. Men are, it's like, hey, can I teach a course or something like that? They're all really good programs. Awesome people. Carrie Joy is in charge of PyLadies. And what's her name? Her last name's Farmer for Girl Develop It, SLC.
Stacy?
Yeah. I don't know if she's still the head up of that, but she's my contact for them. Stacy Farmer. Salt Lake City, slcpi.com. It's down. I still haven't been able to figure out how to get it back up. I don't know what server it's on. I lost the server. I'm really sorry about that. I'm going to put this on a GitHub static hosted. That's my plan this month. So then it's just up. I might hand that over to my dad because he's looking for a project. So, let's see.
Busy rather than go insane.
Yeah. Let's see. We also have GitHub repos. If you have a presentation, we try to fork it onto that. This GitHub repo is in charge of. You guys see that? So that GitHub repo is in charge of the of Utah Python. So you can edit that and send a pull request, and that'll actually just refresh and upload straight to the utahpython.org. So our sponsors today are Pythonistas like you. Thank you very much. Give yourself a pat on the back. Woo! Xmission. I keep asking Matt if I can do the spiel, and I always come up with something, and Matt just face palms. So, Xmission, they won't spy on you. Xmission, Twitter isn't extra. What else? Xmission, they are open tubes for the public and super fast. Xmission is your local, organic, homegrown, friendly internet provider. If you have a company that wants to sponsor, they're always appreciated. Team has been sponsored. They sponsored a couple raffle prizes a couple meetups ago, and they hopefully will be sponsoring more raffle prizes in the near future. And yeah, new sponsors are always appreciated. Just send us a message on Meetup. So, before we do new members, I am going to do something kind of solemn. I'm sorry about this in advance. As you know, one of our sponsors is the University of Utah. They lost somebody who could have potentially been sitting here today. So if we could just take like a few seconds of silence for that person. Okay, thank you. So, as you know, that happened. And what I like to do when you're introducing yourself is I always do something like non-code, okay? Because computers aren't the thing, they're the thing that gets you the thing. Programming isn't the thing, it's the thing that gets you the thing. It's like you only got one life. So, new members, raise your hands. So today we got a lot of new members, which I'm really happy about. So you're going to name yourself, hopefully you have a name. You're going to go over your occupation or what you're doing right now, like if you're a student or if you're just like a hiker. That's kind of cool too, because you don't really do other stuff. And then let's name 2 things you're thankful for. Because of course it's November and we got to do that. But and this time I'm going to let you do something codey and non-codey. And you can't say Python. We're all thankful for Python, okay? Yeah, so I'm Ferris, for example. I'm the senior backend janitor at Team. I clean up other people's code all day.
We have a job for you.
Yeah, I know, but I can't do COBOL at Hill Air Force Base. I'm sorry. No, but yeah, that's what I do.
Nice.
2 things I'm thankful for, non-code. I'm very thankful for my partner. She's awesome. She's right here. I'm thankful for all of the things that we've done this year and to have some support like that. Code-wise, I'm really thankful for PyCon, because PyCon in general is just awesome, because it's like Python itself wouldn't be Python without the community. So yeah, that counts as my code thing. Sweet. Who else is new? We'll start with you.
My name is Casey Johnson, and I do data warehousing. I'm the director of data services for a company called SEMA Credit, so it's a fintech company. So a lot of data warehousing and data cleansing and all things data. 2 things I'm thankful for is Redshift. You guys are warehouse guys. Redshift is awesome. So I'm really thankful that Amazon built that. And non-code, I'm thankful for the invention of wake surfing. It's a good way to get away from the code side of what you're thinking for.
Sweet. And you get to pick somebody else who's new. So raise your hand, new people.
Right here.
My name is Jarrett Swar. I currently work as a business intelligence engineer / DBA. I'm thankful for my cat, and I'm also thankful code-wise just for the data itself, because we can determine we wouldn't have a job, and also it's just, the data's great. How to really describe how great data is.
Oh, and you get to pick somebody, so.
You're in the back.
My name is Mason Chu. I'm currently about to graduate, and I'm looking for a job. Someone hire me, please. But yeah, I'm graduating with like a bachelor's in computer science. And I guess something new that I'm thankful for, I've just discovered, is red pencils. Because I've been sketching my whole life, but then someone told me you should sketch with this pencil, and that like changes everything, and I don't know why. So, yeah, that's amazing. But, yeah, that's
Hi, I'm Justin Parnell. I'm a division leader for McKinnon Mulhern. We're a business communication firm in Salt Lake, so I'm actually a writer by trade, and I program to take a break from the written word. So what I'm thankful for is 2.5 more years of life support for Python 2. So I don't have to learn anything new.
Did they add another 2 years? Or?
I thought it was April 2020.
Yeah, 2020, okay.
So
Yeah.
that's 2.5 years. Come on, we gotta.
A lot of packages are gonna sunset before that, though.
Oh, is that so?
Yeah.
Well, learning's good, right? And I'm thankful for learning. No, I don't know. I'm thankful for opportunities to be able to combine writing and programming. I think it's a really cool confluence. So it's kind of coding related, but art stuff.
Pick on somebody else who's new.
How about wherever you got me in?
Hey everyone, I'm Genome, and I'm a PhD student in bioengineering. And I do discovery from data for helping people who have some sort of medical issue. I am thankful that, thankful for our beautiful outdoors, and coding-wise, thankful that I'm not going to have to program in Mathematica once I leave grad school.
True. That's too real.
Hi, I'm Miguel. I'm currently a production assistant at a TV series producing in Park City Film Studios. I'm thankful, code-wise, because I'm thankful for the fact that I have a job that is allowing me to get closer to this field, despite that my major was not exactly computer science. And code-wise, I'm thankful for all the online resources that are available right now, like edX and Coursera, because they're really helping me get closer to my career goals. Yeah.
Miguel, I'm going to let you know on a secret. Miguel, right?
Miguel.
So I have a BA, so don't tell anybody. And by the way, who here does not have a degree in computer science? Just, yeah, so welcome to the club. Raise your hand if you're new.
I'm Daniel Willis, and until Friday I'll be a dev at OC Tanner, and then starting on Monday I'll be a dev at Big Squid. And I am thankful for a non-Python thing for F#, and I'm thankful for people who organize and sponsor meetups so that nerds have places to go.
Thank you. That means a lot. Thank you. Who else is new?
My name's Spencer Ashby. I got a degree in biotechnology, so I did some bioinformatics in college. But I currently work as an analytical chemist, so nothing to do with computers. But something I'm grateful for code-wise is just meetups like this. My dad, he kind of introduced me to Python. I'm a serious beginner, but kind of excited to learn more about it. And non-code-wise, really, I guess, grateful for family.
So I'm Tom Ashby. I'm Spencer's dad. I was a software engineer. My career worked at Intel. All the coding that I wrote was in C, C++. I retired about 7 years ago and found that I was actually a codeaholic, so I couldn't stay away from it. So started picking up other languages, and when Spence graduated, I introduced him to Python just for the fun of it with a Raspberry Pi. And
nice.
He's been having fun with it. I'm grateful for, like Casey said, Redshift, but I'm actually grateful for solar redshift stars, and that changed my whole life about 3 years ago. And I'm grateful for family as well.
Sweet. Who else is new? Way in the back.
Hey all, I'm Vikran. I'm a PhD student at the U. My office is just like 2 stories up. I work in astronomy. Code-wise, I'm thankful for the University of Utah because it's a member of a big survey called SDSS, which is like a galaxy survey. So we have like tons of data, so I'm very happy for that because I get to work with it. Non-code-wise, I just like the weather in Salt Lake, so I enjoy that.
Really? You like the changing weather? How it's like summer and then winter?
It's better than where I live. Yeah.
Fair enough. Fair enough. Anybody else new to this here meetup? In the back.
I'm Johnny Williams. I'm an engineer for LDS Church and Endpoint Management. What I'm thankful for, family of course, and code-wise would be everybody who put courses and tutorials online. That's helped me start picking up Python as I'm learning it.
Who here is self-taught? I'm just taking random polls today. Yeah, that's pretty awesome. Okay, anybody else who's new? I know somebody back here is. Don't think I overlooked you.
My name is Rocky. I am not a programmer at all, but I'm a biologist. But I work with a lot of programmers who use Python, so I'm really grateful for them code-wise because I don't really know much about it, but I'm learning. And code-wise, I guess I'm grateful for Netflix.
That's still some code, right?
Yeah, I guess so.
Awesome. Anybody else new? Going once? Going twice? All right. Speaking of biology, by the way, that was my original major, and then I switched to cognitive science. But while I was in bio, this book was awesome. And it's funny because this book's from 2009, but it's still, and I know it's Python 2.7, but you can always update the examples. It's still pretty fantastic. This is what they used to figure out some additional speciation, like in DNA that they found in some biped mammals. And they were like, hey, what are these? And it's like, oh, they're kind of related to us. That's cool. But anyway, this shows you stuff like DNA sequencing, has some really good ways to do imaging on DNA. I don't know if we'll be covering that. No. So.
Alignment today.
Oh, sweet. That's chapter 12. Multiple sequence alignment. So. Yeah. So, let's see. There's a really good picture in here. I haven't seen this thing forever, though, so let's see if I can find it before I waste everybody's time. It was the most beautiful picture of corn I've ever seen. I know. Ah, here it is. Okay, you can barely see it here. Maybe I'll have people, if they want to look at it anyway, but it's part of the chapter on chaos representation. But each of these columns represents a different kind of angiosperm, which is like the flowering plants. And then some of these rows are, so there's like a couple, like these three are like maize, and then they take different organisms that are still maize, but I don't know, they're not subspecies per se, but it's still interesting to see the slightest variation in this picture. You can barely see it. But anyway, it's pretty awesome. If you want to see this later, let me know, page 359. But yeah, I love that book. I started with Ruby, and I had a different book that taught you how to do a Rails app. And then I stumbled onto this book, and I started reading it through. I was like, Python's so much easier, because the first chapter is like chapter 0, and it teaches you a bit of Python. And yeah, lots of nostalgia with that book. All right, let's see. Okay, we're good. What else? Where'd we go?
Who's hiring?
Ah, yes, this fun part. So who's hiring? Team is hiring. That's the company I work at. They're looking for everything from a QA lead to a product lead even. They're looking for a lot. So they're hiring like crazy. They're looking for a director of technology even. So if you feel like you're senior enough and you've managed enough people, go for it. Who else is hiring? Anybody know of anybody who's hiring that I can put on this here page? Nobody? Nobody knows of anybody hiring right now. Did Q4 hit and they're like, oh, we're out of money? Oh.
Pretty much.
Yeah.
January that started.
Yeah.
Our organization up at Hill is looking for people.
What's the name of it again?
It's
Oh, you said to use, what was the site?
USA Jobs.
USA Jobs. But if somebody is interested in working in our group, and we do a lot of C++, C, some Python, some Ruby, some displays. If you would be interested in this, you can talk to me afterwards, and I'll see what I can do about get you in touch with the right people.
Sounds good.
There are some drawbacks. One being that it takes a while to get hired on, and usually we go through a third party to a contractor to hire you on as soon as we can, and then try to switch you over to the government. But and also in our organization, we are a lot of our work is classified, and it takes a hell of a long time to get that stupid clearance. So you're stuck off doing something else for a while. Those are the two main drawbacks to it. But
yeah,
there's good security,
Good benefits.
good benefits.
excellent. Anybody else know of people hiring around the valley or in Utah? No? Yes?
Backcountry is hiring.
Backcountry. They're always hiring, aren't they?
Domo and Vivint, I think, are also looking for data scientists.
Yeah, I remember hearing about that for Domo. Have we seen that okay? Okay, good. Did I spell Vivint correctly? See, that's why I can't work at Vivint. So. Anybody else? Know of anybody? Going once? Going twice? Awesome. Here's a fun part. Who's looking? This is the part where you get to stand up and market yourself. So, go for it. And I will probably fumble your name/email.
My name is Jarrett. I've got about 2 or 3 years of experience working with some DBA, some as BI engineer, use the Kimball method, certified with the MCP right now, going for the MCSA as a database developer. Just looking for like BI jobs and database administrator jobs currently. Pretty versatile, I like to learn quickly and it's fun.
Sweet. And if you have a chance later, you can put your email on here, or you can grab somebody with a computer, because, by the way, this is a public Etherpad, so as I type on my side, it pops up over there. I'm actually using Firefox to type into Chrome, which is...
Oh, and I'm here to see if I want to pick up Python for ETL.
Nice.
You do.
I know a few ETL people. It's true. Anybody else looking?
I'm Jared. Last month I told you guys I was looking to get a job closer to Salt Lake because my wife is pregnant. 10 days ago got laid off by the company I was at. So now I'm really looking in Salt Lake. So I've done a lot of data analytics. I used to work in marketing before I moved into like programming full time. I really like the data side. Pandas, NumPy, scikit-learn, doing a lot of like machine learning before they laid off 10 developers. They have 1 left. So good luck to them. I'd love to stay on the data side, but I do know like full stack web. NoSQL as well as like SQL databases, so let's do it.
Sweet. I actually just realized that your company put out a thing, right, Lexi? Health Catalyst put out a call for data scientists on their Twitter.
I don't know.
They did.
Health scientists.
Health Cat Owl, right?
Has been putting out a lot of jobs.
And we have a good contact there. Then they come over a lot. So if you're looking for a good data science gig, you can't go wrong with Health Catalyst. And then Levi actually gave a talk here a little over a year ago, I think. So it's pretty good. Anybody else looking?
I'm Ted, and as I said, I'm a PhD student, and I'm planning to defend like early next year, so looking to start a job like February timeframe. I'm in data science. I would like to discover from data side of things. I'd like to stay in the biomedical field, but I'm not totally set on it. So generic data science would be okay as well.
Sweet.
So I do know one company I forgot. It's a company called Kinestral. So
How do you spell that?
Kinestral. Yeah. They do automated glass. And they're looking. Yeah, so like you can walk into a room and say,
oh yeah, the polarized glass
Alexa,
stuff.
dim the windows, and the windows dim. They're looking for a data scientist doing machine learning. If you're interested, I'll get you in touch with somebody.
Sweet. Who else? In the back.
Hi, my name is Manson. I'm fixing to graduate this December, bachelor's in computer science. I'm pretty much a full stack developer, and if there's a language I don't know, I could probably learn it pretty fast. Let's see, and I'm not particularly I don't really specialize in data, but I can do it. And I feel my preference at the moment is more development of software and stuff. So yeah.
Sweet. Anybody else? Oh yeah, this guy.
Good. I did it for you.
Oh, okay.
Hello. This is my third month here that I'm looking. And actually, I just finished up this week with some career counseling companies who helped me rewrite my resume, set search options. It's complicated out there, you know? So I'm on LinkedIn, I'm on Indeed, I'm on Glassdoor. Practically, you name it, I'm on it. But right now, I'm thinking the best course of action is probably to go for the direct contact. So, gentlemen, you were saying you know something out at Hill? Well, Hill's close to me. And,
yeah, right.
And but realistically, what it comes down to is the biggest. This is something that I never thought I'd say. I've always been proud of being a generalist. Now it's at the point I look at the job and say I could do that, but then you turn around and you say, how do they know I can do that? Yeah. Okay. So. That's what it's about. Being a generalist is a good thing because it means you can do practically anything, and you're always learning, but try to explain it to somebody else in the 15-second elevator pitch. Thanks, guys.
Sweet. Anybody else looking? Now's your chance to market yourself. Everybody's happy with being a data scientist at other places? I was going to say at Overstock, but no. I'm just kidding. Sweet. Community news. There was something that turned into version 5, but I forgot what it was called. Hold on, let me check my email. I got an email about this.
Can go rest framework to send an update.
Hooray! Another one. Was it SciPy?
SciPy 1.0, I think.
That was last, but yeah, that's still pretty cool.
I don't know what's out of post on recently, but I could be way behind.
Let's see. PyCoders Weekly. That's by the way, that's where I usually get this stuff. Is anybody else on PyCoders Weekly? It's a pretty good mailing list, yeah. They have fun little names like Loops, Fellows, Avenue, Tiger. I don't know how they come up with them, but they're pretty fun. What was it? Oh, and they also have job postings all the time, outside of Utah, obviously, but still. Oh, Anaconda 5, that was it. And Pandas 2.1. Anybody use Anaconda? Yeah, it's pretty handy. I used to set up Docker images to do all that. And yeah. Oh, it's 0.21. Okay.
So Pandas 0.21 is actually added support for saving to parquet format data straight from a data frame, which compared to the previous best you could do, you can decrease the size of your data frame stored on disk by about a factor of 2.
Did I spell parquet correctly?
That 3 times faster at the same time.
Yeah, that's cool.
I spelled parquet correctly. Out of all the things today that I'm going to misspell, please note that I spelled parquet correctly. Sweet. Let's see where we're at. Anybody know of any other community news, Python news, server news, Linux
Rust
news?
framework just had an update today. To 3.4.7 or whatever.
4.7?
3 point something or other.
Has anybody tried API Star since I gave my DRF talk? Anybody?
Start poking at it.
Hmm?
That's interesting.
Yeah, just poking at it, you're like, oh, okay, this is how you're supposed to do type hinting. This is cool. I can't shut up about it. But it's also a really cool community that they set up with the Discuss, I think is the name of it. I don't know, not Discuss with a Q, but anyway. But it's a pretty cool forum. Really helpful people. And then Tom Christie's constantly talking to people on it. He's a really friendly dude. He's the author of Django REST Framework, by the way. Sweet. New topics, new speakers.
Actually, I'll get it out of the way. Probably all the data scientists know this already, but the big data.
Oh yeah.
Big Mountain Data Conference.
I saw an ad for that when I was stuck on I-15 today. And that's the 10th and 11th?
That's right.
You can go to Utah Geek Events and go register, and it's just downtown.
Yeah, it's
over at
free.
the Apple's building. Yep.
It's free to attend and lunch is provided as well. So you got nothing better to do those days and you're hungry.
Is that why you're here? Sweet. So we actually have a talk for December, so I'll update this. Let's see, and it's not the 1st. It's going to be the 7th actually for this January. Next meetup will be the 6th. But anyway, we're going to have some guy do some talk about things, right?
Yeah, I'll be talking about things.
Yeah. I already announced it today, this morning. It's going to be, what was it, time series?
Yeah, into the time series forecasting, more of a business into it, but using Facebook's new profit framework for forecasting, which is pretty awesome.
Sweet.
So
if this was the Silicon Slopes meetup, we would probably add some kind of clickbait title, like impress your boss with analyze graphics and predicting the future. Like, I don't know.
Yeah, make billions in your
Yeah, make billions. Sweet. Anybody want to give a talk in January? You have plenty of time now. It's next year, so. We won't be having a talk in February, just to reiterate that point. So February, we're going to just get together, have some pizza, have some beverages that may or may not include beer, and give away a ton of Raspberry Pis. So it's actually a lot of fun. We get some pretty good sponsors there, and it's also our fundraiser, so we have money for the end of the year, and I don't look at red numbers all the time on our money page. So yeah, that will be in February on the, who's been to one of those before? On the 7th, by the way. Yeah, they're fun, right?
Mm-hmm.
We might do it at Mellow Mushroom again, but I'm not sure. We might do it at the Pie. That might be fun to just go to that pizza place. That venue's a little bit tiny though, so I don't know if they could host all of us. I don't know. I'll probably put out a poll / ask everybody. Speaking of poll, I had another hopefully last polling question before we take a quick 2-minute break. So I noticed that a lot of people start showing up around 6:30. Would anybody be, raise your, okay. Who would be for having the pizza at 6:30 and starting the talks around 7? Does that work for everybody's commute? Who cannot commute in that amount of time and it just doesn't work for them? Okay. Oh, one person. Now I feel bad.
We're good.
Okay. So say we all. So I think I'm going to start and switch things over to 6:30. Should be. Hopefully it'll work out. It should work out. Plus we have like daylight savings is about to end, so maybe that'll change people's schedules. But anyway, yeah, so we'll switch it over to 6:30. I'll try to get the pizza here by 6:30, and I'll make sure that our venue peeps. Martin, does that work, you think, for you? Yeah? Sweet. So yeah, I think we'll start doing things at 6:30 for this meetup, and that way we're not here until 9 too often, unless we're having like a grand old time. Sweet. Let's take a quick 3-minute break. What do you have?
One thing. Utah Python North in 2 weeks. We're going to do Minecraft plus Raspberry Pi.
Oh yeah, that's a fun talk.
So come join us.
Yeah, so you can use Python to code certain, like a turtle-like thing
6:30.
in Minecraft.
But we don't start till 7.
What day?
Wednesday. Oh, yeah. We can put it off. If people want to come, we can put it off till 7 start.
All right, we're going to take a quick 3 to 5 minute break because Garrett and I need to sync up our laptops. So.
I went in 5:30.
Oh, fun.
What kind of inputs we got?
We have everything under the sun. It's
Is it all
VGA.
the Windows
Yeah. Can you move a little bit closer this way? That's the part I'm worried about.
I'm so busy with security stuff.
Yeah, I can't go further on this one.
Yeah, you haven't got back to
Oh.
it.
No, it's thank you.
The long cord?
Yeah.
That one's broken.
What is it?
Yeah, I tried. Yeah.
Busy.
So what do you do right now?
So I work for a company that automates bioinformatics analysis stuff.
What's it called?
Called Genome. You've never
Nice.
heard of it because there's only like 9 of us.
How long have you been doing that? I'll move over too.
February.
So he come here a
How long
lot.
have you been doing bioinformatics?
Since February.
So he back out.
But I'm trying to put a lot of time into stuff. I'm interested at least a little bit.
Yeah, me too.
All
the data science.
So I stay connected. This stuff. And then I need you to do a screen share to a Hangout call so we can live stream this. That's the tricky part.
Now I've got you on the chat. Now whose job is chat?
Yeah, so do video chat.
Like I always try to get that documentation. So you have to explain this to me so I know.
When I
oh, is it a subject?
Not good enough.
Yeah, it's a company called ZeroMQ.
And then over here, you have all
We write a bunch of software.
Come on. Oh, you're still calling it that one.
Recommendations.
So what about you?
I work for a supervisor. It's a food drug retailer. They're based in Minnesota. So I'm like a solo.
Yeah. Remote.
Yeah. And so, but I'm sure this is a lot of the same things. Recommendations and podcasts and those that's what I'm for. And very much, I just data warehouses and campus. Yeah. Going elsewhere? Yeah.
They got rid of it.
Yeah, so I met her. My brother-in-law works for as well.
No, it's usually right here.
He does a lot of
oh, there it is.
Yeah, sometimes.
It's going to ask you like 3 different times. Connection might be.
Yeah, so they brought me in because we use the same phone system that they use in contact.
So you click application.
I will get to that position. I want to get my portfolio, check all my clients and users and Thank you so much. Okay, we'll see you next month.
Oh, no, I can't.
Microwave came You need to try my micro to regular size HDMI and then do it.
Smart. Oh, so we have to actually introduce ourselves.
Yeah. Hey, how's it going?
Good, Ted. So,
yeah, why don't you give me, I'll text him too to tell him that you'll be emailing him, but I don't have the card.
Alright, I can give you. I have one.
Well,
yeah,
I'll just take a picture of it. And
either one is fine. I have that for home.
Okay.
Just want to make sure I wasn't giving you two. Yeah. Shoot me your email.
Yeah, I'll shoot you an email with his contact info.
Okay, you are good to go.
So yeah, cool. Yeah, I'll email you tomorrow. Give you their contact info. And then just shoot out your resume.
All right.
Fantastic. Thank you, Casey. Yep, thanks.
So sorry about that delay. Display issues, you know, like printers and display issues. So just wait for 3D printed displays, then it's going to be like terrible. So Garrett is a. Oh, is it not working?
That's one tall layout.
Okay.
Yeah.
Then you're good to go?
Yeah.
Is the thing working?
Hey.
Okay, so Garrett is a bioinformatics by trade, but he was forced to become a bioinformatics person.
No, I chose to.
Oh, chose to in February, forced to. He's telling everybody, just don't tell. Anyway, and he offered graciously last month to give a talk about bioinformatics. I told him about this awesome book, and I was like, hey, if you do that talk, I will get this book for our raffle. So, look at that.
Cool.
Here we are today.
It's a good book. I've read a good chunk of it since then.
Let's all give a warm round of applause.
Thank you, everyone. So, just a little.
Move the camera around.
Oh, out of the way? Oh, yes.
We're actually streaming the screen thing, so that's not doing anything right now.
Okay,
good. All right. So I'm Garrett. A little bit about me. I went to the U here, graduated in physics back in 2015. So I spent some time in this building. Upstairs, there's some physics and astronomy stuff going on. Ended up working at a place called Myriad Genetics up the road. They do mostly like cancer predisposition testing. From there, learned a little bit about what bioinformatics was, decided it sounded really cool. And a year and a half-ish ago, I started a master's degree in bioinformatics. I'm doing it online. Still working on that. But then about a year ago, I had my first course where I actually really used Python. So really, I've only been doing Python for just probably about a year now. So if you're a beginner, you can only start something in a year. I don't know how good I am, but I feel like I've learned at least a lot that's useful to me. Before that, I'd done a little bit of R and stuff like that, but no Python. And then in February, I managed to con my current company into taking me on as a intern to hire position. So I quit my stable job, which was really scary to do intern for hire. They liked me enough to hire me, so I'm still there, luckily, working as a bioinformatics developer. We automate some of the stuff we're going to talk about, and then some other stuff too. In the cloud, we use AWS. That's what I do on my day-to-day. Probably not going to talk about a lot of that today because it's kind of boring for stuff like this. It's not a whole lot of, you need a lot more background. But today we're going to talk a little bit about bioinformatics. So I think every good talk starts with XKCD, right? So if you read it, it says, this guy says, biology is largely solved. DNA is the source code for our bodies. Now that gene sequencing is easy, we just have to read it. So she says, it's not just source code. There's a ton of feedback and external processing. But even if it were, DNA is a result of the most aggressive optimization process in the universe, running in parallel at every level of every living thing for 4 billion years. That's still just code. Okay, try opening google.com and clicking view source. Okay, that's just a few years of optimization by Google devs. DNA is thousands of times longer and way, way worse. So yes, biology is impossible. But we are going to try and take a little bit off of that today. So, oh, by the way, on the bottom of the Etherpad, where Ferris was editing everything, I put the link to these slides, also the link to the GitHub repo where I put all these slides. It's a Jupyter notebook that I just made into a slideshow. You should volunteer to do a talk, because I didn't know how to do that a month ago, and I had to learn how to do this. So it's a good learning experience to give a talk. So, what is bioinformatics? So according to Wikipedia, the authority on everything, it is an interdisciplinary field that develops methods and software tools for understanding biological data. Well, all of these speaker notes are available on that slide too, so if you want to If you go to that website and you hit S, the speaker notes will pop up, and a bunch of these sources and stuff that I'm going to quote to you are going to be there. So another definition that I actually like better is by Frej Tikaya. Says, the mathematical, statistical, and computing methods that aim to solve biological problems using DNA and amino acid sequences and related information. So basically, DNA, amino acids, what can you get out of it? There's a lot of them. What do you do? So what is DNA? I'm going to start out a little basic here. Our biologist back there is going to be bored for a little while. So long string of A's, C's, T's, and G's. So basically, what is it about these that needs all these computational methods? Well, I'm here to tell you that nature has been playing with big data long before big data was big data. So there's a lot of big data going on in your DNA. So DNA is the source, basically your source code. It's what makes you you. So we're going to talk about how that works in a minute. But first thing you need to know is a whole bunch of A's, C's, T's, and G's. Those are 4 different kinds of molecules. They have really long names that nobody ever uses anyway. We're just going to call them A, C, T, and G. If you're interested, you can find it on Wikipedia. And I'm also going to call them bases because that's what we call them. It's just a term. When I say base, I just mean one of these molecules. So like one A is just one base. If I have like a string of A, C, G, T, T, C, A, T, G, G, that's a string of 10 bases. 10 bases, 20 bases. Except it's not really a string because there's 2 parts to DNA. So when I say like the one sequence, I'm talking about one side. But the really nice thing is on one side you know the other because A's and T's always match up with each other, and C's and G's always match up with each other. So if you know on this side you've got an A, then on the other side you've got a T. On this side it's a G, on the other side it's a C. So you really only have to know one side because the other side's just whatever the complement is, which is kind of nice for reasons we'll get into later. You don't have to store all of this data because that would be even worse. So now you know everything about DNA. But anybody have any guesses how long the human genome is? And genome is just a fancy word for all the DNA in your body. Any guesses?
300 billion?
Luckily, not that long. So it is 3.2 billion base pairs long. I say base pairs because there's the 2 strands. So 3.2 billion base pairs long for us. We're actually not even all that special. A lot of plants are a lot longer than us. This is a plant called Paris japonica, which may be a contender for the longest genome at 150 billion base pairs. So luckily we don't have to deal with that because it's unruly enough as it is. But what does all that even do? I was going to tell you. So this is, I think I did this so that it's PEP8 formatted, so 79 characters per line per PEP8 guidelines. And it's still going to be 40 million lines long. So that's quite the code base. What does it do? Well, a lot of it doesn't do much that we can tell. Does anybody else's code base look like that? We'll stick with about 1.5% that we have a pretty good idea of what it does, which is not a lot. I'm going to say that other 98.5% does stuff. We just don't understand a whole lot of it just yet, but we'll get in there. So we're going to learn about something called the central dogma of molecular biology. So molecular biologists have to have a fancy term for what DNA does. Basically, we're going to go over just the basics. Transcription, translation. You've got your DNA. It replicates, you grow, your new cells get DNA in them. That's kind of boring. Transcription. DNA comes into something RNA, which is a lot like DNA, but a little bit different. We're not going to worry about the differences right now. But the nice thing is you can use RNA. So basically, your DNA codes for RNA. Your RNA is a code that turns into proteins. And what are proteins? Well, basically all of what you are is either protein or proteins make it. So that's pretty much what makes you up. So the DNA tells your body to make protein. These proteins make these little machines combine into bigger machines. Basically, bigger and bigger until you get to the whole organism, your whole body. How do little parts all know how to fit together? It's a good question, and we're not going to go into that today, but there's some really cool stuff there if you want to look it up. Sequencing DNA. So now that we know some of the, now that we know some about DNA, we can kind of see some of the fun puzzles that DNA presents to us. So one of the biggest ones is, how do I know what my DNA is? If I wanted to say, okay, what's my DNA? How would I do that? Well, there's a lot of different ways. There's some cool new ways that I can talk to you later about if you want to, that use some new methods. But we're going to talk about the most popular one right now, and that is Illumina's sequencing by synthesis. Illumina is a really big company that does sequencing, that writes really awful C++ code that I had to debug the other day, and it was really awful. But basically, what's the strategy when you've got something that's going to take a really long time to do? What do? We want to parallelize it, right? Yeah. We want to break it up into little chunks and do all little chunks, because nothing ever goes wrong when you do that, right? But in this case, the trade-offs are worth it. So basically, you just take your DNA, break it up into little tiny chunks, and then you mount them on this thing. And so, you also split them in half. So you know how we talked about how they pair together? So you mount one half on the slide, and then you have, you put it on the slide in a special machine, and then you flood it with, say you've got a whole bunch of A's, remember the bases we were talking about? So you just flood it with a whole bunch of those, but they're special ones. They have something, they're modified just a little bit so that they light up when you shine something on them. And then they also, they light up a certain color, and then they also are modified so that nothing else can attach after. You can only attach one at a time. So basically you flood that on, wash all the excess off, and then you take a picture when it's fluorescent and say, okay, which of all, the whole ton of little tiny chunks on this slide had an A added when we did that. And then you do it with a C, and a G, and a T. And then you repeat it a whole bunch of times, which takes a long time, but not nearly as long as if you had to do everything all sequentially. So we're going to, just real quick, because that might not have been the clearest explanation, see if this works. It is really cool that you can...
Sound will not work, just FYI.
That's fine.
Okay.
It's really cool that you can import YouTube video on Python. Python's awesome.
I know. Jupyter is so cool.
Yeah, I know, huh? I can full screen it. So, this is this is doing it a lot faster than it would be. So, you put on a T, it shined red, they got that. Put on an A, it shined blue, they took a picture of that. Basically, the pictures are what you use to do all this stuff. So, that's all we really need to know about that. Where did that escape key? No, not that, no.
Press F.
F.
I had switched caps lock and escape. I keep forgetting. I have my own custom stuff.
I should.
If you use Vim, you will probably switch caps lock and escape at some point.
That's
I actually use caps lock. I have lots of capital A's, T's, and G's.
What do they call that? Pinky? What do they call that? Pinky syndrome?
Well, who uses caps lock?
I have lots of capital A's, C's, and G's.
Yeah. You're the only field that you would use caps lock.
Doesn't use caps lock.
Use this guy now.
And I lost my focus.
You really switch your keys from?
Yeah.
That's hilarious.
I mean, not Dvorak, because I'm not unemployed.
Okay, so now things start to get fun. Now we've got a whole bunch of little tiny fragments that we know what the sequence is. Then what do you do with it? So, this is a nice looking lake. Looks like someone you'd want to visit. Now how do you like it now that it's a puzzle? That looks like a pretty hard puzzle. What makes this such a hard puzzle?
Reflection.
Yeah. It's blue everywhere or white. It's hard to tell what's what. So it's basically kind of like that. We've got what's called a reference genome. So basically, this is what we've said. This is what humans have. Like, this is the DNA of the standard human. There's some problems with that, but it's used a lot because it's pretty easy. I read today, I think it's an African-American guy from Buffalo, New York, comprises most of it. Trivia for today. So basically, what you want to do is take all these little tiny chunks and line them back up to this 3.2 billion base pair long genome, which is quite the computational challenge. So we are going to talk a little bit about, we'll introduce the algorithm a little bit, and then we'll see how we do this algorithm in Python of sequence alignment, basically what we call it. So first thing we're going to do is assign scores. So this is going to seem like overkill, just for a minute until we get a little further, and then you'll realize why we set things up like this. So this is our scoring matrix. If you line up an A with an A, it's 1 point. Everything else. If you line up anything else, you don't get any points. So this one has 8 that match up, 8 ones, alignment score of 8. So next step. So if you, what if you had 2 of these sequences? Could you get like a better score, maybe by like shifting a little bit back and forth, maybe something like that? Yes, but there's also another problem you have to deal with when you do stuff like that, and that is gaps. So one unfortunate thing about sequencing DNA is it's not super accurate. There, mistakes happen when you sequence 3.2 billion base pairs worth of stuff, and so you'll like be missing a base, or you'll have an extra base. So you'll have like gaps in one. So this really does line up to the other one, but there's some missing. So you got to account for like the missing pieces. So, or the other thing is humans are different. You may be missing, a base compared to some other person. So we're gonna have a gap penalty. So every time you have to introduce a gap, we -3 from the score. So this alignment, even though they look like they're pretty well aligned, it just has an alignment score of 1. Where did my notes go? Oh yeah, this is the out-of-date one. I had an update on my laptop, but my laptop's not working. But it should work anyway. So this is a scoring matrix. So we're trying to align this sequence to this sequence. And basically what happens is, so like say we line up an A with an A, then we do, so if you line up these 2 sequences, then you do the score from the upper left, the one that's up and to the left of that box, plus whatever the alignment score is. So for like here, it would be 1 because it's 0 plus 1. But like for this A up here and the C right here, in this box you would have, for that one you would have -3 plus 1 -2. But that's only one possibility. The other that's if everything actually lines up. If you have to introduce a gap, then you come from the side. So if you introduce a gap on one of them, then you do -3, -3, which is our gap penalty, -3, -3. Oh, these all got filled in because you know that these are just going to be only gaps. If you line up this, absolutely nothing on this one, then it's just all gaps. So what you do is for this square, you calculate what the score would be from a gap here, what the score would be from a gap here, and what would be the score if you actually line them up. And then you put the score in the box. So the problem with that is once you start doing these ones down there, these scores depend on the path you got to from up here to get to these scores. So you got to put in arrows. So you know that I got this score. This score was the score I calculated out of this box. And this score was the biggest score out of this box, this one, and it came from this one. All right, so then this is one of those all filled out. And then you basically follow the thing from the bottom right corner, match up, go up 1, they match up. Let's see. Where am I going wrong here? Oh, it's because it got cut off the actual corners here. Sorry. So my screen got cut off, so there's actually an extra base over here. So this one goes to here, they match up, those G's match up, but then since you got a sideways arrow, that's that gap right there, is that sideways arrow as you follow that path. Follow it up all the way to 0. So let's do some Python code for this. So this is our, this is the same little matrix we had before. We use NumPy today. And then this AC to G and T is like what went along the top and along the side of that matrix right there. And here we are going to calculate, so you know how we had like a matrix of scores, or we had the scores and the arrows all together in that one big matrix. It doesn't work so well to try and calculate two things in the same matrix in Python, so we end up making two, a score matrix and an arrow matrix. So this looks long and dumb, but all we're doing here is just creating an empty scoring matrix up here. And then, oh, by the way, I borrowed a lot of code out of chapters 7 and 8 in this book. Updated for Python 3, and then just also updated it because code's a little weird, I thought, but still good stuff. So then you basically go across, you go row by row by row by row here, and you calculate what the score is from the cell above, plus the gap penalty, our -3 right there. To the left, to the upper left, pick which one is the biggest, and stick it in there, and then in the arrow matrix, we stick just a 0, 1, or 2. And those are kind of showing which way our arrow would be for that matrix. So what would our results look like? So if I align this and this is our score matrix. It's our arrow matrix. This is telling you which direction everything's pointing. So by itself, that wasn't super useful because that doesn't tell you a whole lot. So now we need a function to actually get what we want out of that. Backtrace, basically you're just doing what I showed you. You start at the bottom right corner and either go up, left, or up and to the left, depending on which way the arrow in your arrow matrix is pointing. And then either add an alignment there or add a gap in one of them. And then use and then we make it backwards because we're starting backwards, so we just return that reverse so it's in the original order that you got it. And then this part right here, it's not strictly necessary, but I'll use it a little bit later. And that just tells you where in that scoring and arrow matrix, like which cells your path followed. So you do this function and it spits out, the string and the string. That's how they line up. But sometimes it's nice to actually see the matrix instead of just seeing the strings. It's hard to see. This you can pretty much just ignore because I am really bad at matplotlib and just kind of like fudge through this. But it works. Basically, I'm just going through and putting arrows and scores in for that correspond to the score and arrow matrix. And then I made the path that we actually followed green and bold. So you can see. This is what happens when I stick in my results, is you can actually see the little path right here. You follow to get there, up to there. So, nice little visualization. All right, so how fast is this? How long, if we use this to align all of our little chunks to the human genome, how long is it going to take us? So this is supposed to be 100, because that's about how long chunks usually are. And I altered it on the train on the way here on my laptop. But my laptop didn't cooperate with the AV system very well. So these numbers are going to be exaggerated, but basically I'm just making a random sequence of A's, C's, T's, and G's here. dbed is our DNA alphabet. We have A, C, T, G. And then here I'm just taking that and I'm switching it around a little. So this line is just saying, if 1 in 5 times, it's going to change that base to a different base. And then also, I think I did 1 in 5 times here too. We're going to add a base or we're going to take out a base. So basically it's just going to give you, this is going to give you a sequence and they put that sequence in here and it gives you one that's similar but different. So, because it's boring to align two things that are exactly the same. And this is where what I messed up really got messed up because this is only supposed to be 100 long, so you can actually see the result down here. But if it's actually only 100 long, it takes about, to do this alignment once, or to do this alignment 2.3 billion times, because you've got your one chunk of 100, and you got to test it 2.3 billion times along the genome as you go there. Would take, I think it said 800 something years. So if these are actually 100, that's a much more reasonable, like 4.7 years. Still a long time. And that's for one of your little fragments that you're trying to match up. So you have to do this however many, millions of times, however many fragments you had, depending on how much you were sequencing. So it takes a really long time. So in actuality, you're not actually going to use this particular algorithm to do that kind of thing. You're going to do some cool stuff with some cool other algorithms, but ones that are a little bit hard to model in a talk like this. But this does give you a good idea of the kinds of problems that you have to deal with when you're dealing with these kinds of sequences and stuff. And it's also kind of fun. This is historical. So this was called, I don't know if you noticed the function I did was called NW-align. That's for Needleman and Wunsch. They're the guys who originally published the algorithm. So this is totally historic, like actually was state-of-the-art bioinformatics at one point stuff. But now we use other kinds of algorithms to actually do those kinds of alignments. But let's make it faster because it's not that hard. And sometimes you want to do something like that. So why was it so slow? Well, we had nested for loops. That's a recipe for slowness right there. So one cool thing about this algorithm is you notice. So like this cell, right? Like you can't calculate this whole row at the same time because like this cell depends on this cell. There's dependencies there, so you can't just do them all. But you can calculate a diagonal because along this diagonal, we have, if we start up here and work our way down, we have every up left and upper left for the whole diagonal. So what we can do is get rid of our nested loop, which we're not actually getting rid of it. We're just making NumPy do the loop, which is a lot faster. And so we just loop over the diagonals and then have NumPy do the other loop that goes and calculates everything there. So there's a couple more steps to do it this way, but it ends up being a good amount faster. So first we pre-calculate. These are all of like those, the score to the upper left. This is just a matrix of showing like what's like the score that we match. So this tells you that it's a match here and here, basically all we're doing. And then this is just a little function to give you all the possible diagonals in a matrix of any given size. So a matrix of size 6 and 3, there's the first diagonal, 1, 1, and then there's another diagonal that's 2, 1, 1, 2. Not that interesting. But this is a function that does the same thing. So it takes the same arguments as before, but then uses those two functions we just made in them to produce the same output. But basically all we're doing is, so we have one for loop here, and then when you're doing the, so this is like our, like just kind of an empty array to like hold scores, and then we tell NumPy, okay, calculate all the scores for this diagonal at the same time. So it's doing a for loop internally, basically, but it does it a lot faster. And then you just put all the diagonals together, and how much faster is it? So these are still with that DNA sequence that was too long, so these shouldn't be actually that long. But it was, again, about 4-point-something years for the whole, for 100 bases. This is for 1,000. And this was only like 0.6 years. So, progress, right? It takes half a year to align one thing to the whole genome. So now we're going to talk a little bit about why we use the that substitution matrix. Remember how we had the ACT and GN just had like the ones along the diagonal. So, oh wait, I do need to use that again. I'm glad you put this in.
Yeah, it's on a different screen. Word.
I tried to embed this earlier today, this HTML table in my notebook, and it almost worked, but these lines didn't like showing up, and they're kind of important. So, this is a lot of information, but basically what you need to know is, we talked about how DNA turns into protein, and this is how it does. So if you've got like 3 T bases in a row, it turns into this type of protein. So these are just all the 20 different types of proteins there are. So it's not super interesting, but this is also why, remember how we don't like deletions? So if you have like a sequence that codes for one of these, and you take one of them out, then it shifts everything over one, and then this gets totally messed up. So that's why insertion solutions are bad. especially if it's somewhere where it's actually like.
Close it.
Yes. It's just an extra window, so you should just be able to hold that forward. So we can also align proteins. So this is actually an important thing. If you've got one protein and another, you want to kind of see how similar they are. We're not necessarily aligning to like reference like super long protein like we are with the reference genome, but it's really useful for like telling, okay, these two proteins probably do similar things because their sequences line up pretty well. But it's not a simple like, if they match it's a 1, because there's a lot of different kinds of proteins, and some of them are more similar than others. So like if you switch out this kind of protein with another, it could be not so big of a deal because those proteins are pretty similar. Or those amino acids are really similar. Sorry, I'm supposed to be saying amino acid this whole time. Not protein, but some of them are pretty different. So if you switch those out, then it's really bad. So some scores aren't too bad. Some scores, you get big minuses in here somewhere. This is actually like an actual score matrix that was calculated using like, they surveyed a whole bunch of organisms and said, okay, what types of substitutions do we actually see? Because if there are bad ones, they're not going to happen because that organism is going to survive. So if you actually see it, then it's probably not that bad of a mutation. So that's how they got this. And you can align proteins. So we've got our protein. So each protein has like a 1-letter code that you can use to represent it. You can go along here. Same thing. So that's why we went through all of that weirdness at the beginning, because we made this a lot more versatile, because now you can use it for DNA or for proteins or whatever. Other things we can do with this algorithm, we can do local alignment. So that was trying to like align this whole chunk with this whole chunk, but what if we have chunks and we just want to say like, what's the best matching part of the chunk? So in that case, how we start at the bottom right-hand corner and we snake through the matrix. You just start with the biggest number, and you snake through the matrix until you hit a 0, and that's the biggest thing. And then also, I don't even know how to say this word because I've only ever read it, but gap penalties. Basically, that's just saying if you have a gap, it's bad. But if you have 2 gaps in a row, it's not quite as bad. So you don't have as much. Like your gap penalty varies depending on how big the gap you're in is. But that obviously gets a lot more complicated. But a lot more fun too, if you ever want to play with this kind of stuff. So I'm going to talk about, after this, I'm going to talk about a couple other useful Python tools that I use with bioinformatics. But is there any questions up through the sequencing? Kind of a whirlwind tour of sequencing, but sorry about that. Other useful Python packages. This is one I use a lot. It's called PySam. So basically, there's a C library called htslib, high throughput sequencing library, that is really good at working with these really big files, because bioinformatics is weird, and we store everything in just like files. We don't use databases at all. It's just in a flat file. So it's weird. But this is good at working with those things. So, for example, I have this FASTA file. So a FASTA is basically like, it's a type of file format, it's plain text, of a whole tons of A, C, T's, and G's. And this one happens to be representing the entire human genome. So we've got the whole entire human genome, and compressed, it is 853 megabyte file. So uncompressed, I think it ends up being about 3 gigs. So you're trying to extract, text out of the middle of a giant file. So what I can do is say like, okay, how long is chromosome 17? It tells me it is 83 million base pairs long. 17 is shortest. So we have 23 chromosomes, and in general they get shorter as you go down. So one's a really big one, two's a little smaller. So this is a smaller end chromosome. It's 83 million base pairs long. And say, okay, I just picked a random 500 bases out of the middle of that and said, okay, give me these 500 bases out of the middle of this giant file. And it took 203 microseconds. So that is the kind of speed you need to be able to actually work with this kind of stuff. So that's what's really nice about this, is it allows you to work with these files and actually extract stuff out of them and not spend all day just waiting for your stuff to get extracted. And that includes decompressing it too. So it finds the sequence, decompresses it, shows it to you. Another one is called Biopython, is another package that I haven't used a lot of, but it's really handy. You can put in a sequence, so like a whole bunch of A's, T's, and G's, tell it that it's a DNA sequence, and then it does this whole translating thing, like there's the protein for that DNA. And you just one step right there. That was really easy. So it's got a lot of convenient stuff for that, like when you're working with really long sequences and you're trying to switch them back and forth to DNA, to protein, translating, all those kinds of things. Handy stuff there. This is actually a really huge package that wraps a ton of different bioinformatics libraries. So you can do a ton of cool stuff with this, so you can use all these libraries from Python. I'm not going to go into a ton of that there, mostly because I haven't used it a whole lot, but it's pretty cool. Do we have any questions?
When I was looking into some mice MRA stuff, we used the program Bowtie to do the sequence alignment, and it required some slightly different configurations. Is Python better for that than Bowtie?
No. You want to use Bowtie. So Python's good for modeling algorithms like this, for getting your different. So let me show you guys a slide real quick. I have a couple extras. Oh, yeah, it was this one. So this is kind of, so GATK, that's another program that you can use to do a lot of the heavy lifting. But basically, you've got to start with your raw data that you get off. You have to map it, and then you have to tell which ones are duplicates, because you have to, when you're splitting all of them up, you end up with a whole bunch of duplicates because of something called PCR. If anybody, biology people know what PCR is, it's big stuff, but it's basically just duplicating DNA. Realign it, all these things. So then you've got your reads aligned to a genome, and then you have to say, okay, now that these reads are aligned to a genome, now what? So you have to actually say, okay, for these reads with this person compared to this genome, they differ at this position in this way. So this base is different at this position here. So that's calling variance. And then you basically, once you've called the variance, it gives you another text file, lots of text files. Oh, this is a text file here too, this alignment. The alignment files are all just text files. And then you can do a bunch of stuff to make that actually more accurate. So Python is good at a couple things. Python is really good glue. I spend a lot of my time using Python as glue to make this step, which runs in some C library, to this step, which runs in Java, through this other intermediate step through this. So basically, I'm chaining input files to output files with Python. So do a lot of that. It's good, and it's good for just when you gotta tinker around and stuff. When you've got a file, and I've got to, I've ended up with like, this is a list of positions in the genome. I need every base that's one to the left of every one of those in this whole list. So Python's really good for that kind of stuff when you're just trying to extract data from big data sets as you need them. Bowtie, is it an aligner, right?
Yeah, it was. We used it to align stuff.
Yeah. So it's an aligner. BWA-MEM is like the big human aligner. Burroughs-Wheeler alignment. So yeah, a lot of these tools themselves, you don't want to use Python for, just because it's not really built for that kind of really intense computational stuff. But Python is still really great at putting it all together so it actually does something useful. Does that help?
Yeah.
Okay. Are there any other questions? Yeah.
What kinds of questions do you find yourself answering with this data? I mean, is it like DNA matching? Is it analysis? Or?
Yeah, so our big thing with my company, so how my company got started is we have basically a way to parallelize all this. It's kind of hard to break up, like kind of hard to parallelize it sometimes because your DNA is naturally split up into what are called chromosomes. It's not that important, it just means your DNA has natural separation to it. But they're not all they're not all the same size, so if you use each, the natural separation to parallelize things, then threads end up finishing before other threads, and you got threads waiting, and you got CPU waiting and all that stuff. So that's how we got started. So we got a cool way of doing that. But now that we've got that going, we are focusing a lot on what you talked about, which is basically, when you kind of get to this call-variant step here, so that basically, you get a file of, okay, this is how this person is different from the standard reference genome person. Doesn't matter. Sometimes when you have a difference, it doesn't matter because that section of DNA, we don't even know what it does. Maybe it doesn't do anything. Sometimes it does matter because that section of DNA encodes for a really important protein that will make it so that you're sick. So like a good note, so I used to work for Myriad Genetics. They got started, there's a gene called BRCA1, another one called BRCA2. And if you've got mutations in those genes, then you are a lot more susceptible to breast cancer. So basically what you do with all of this data in the end is you say, like what we're focusing on a lot is, okay, so this person is different from the normal person in this ways. Does it matter? Is this going to predispose them to some kind of disease? Or if they have a disease, can we tell which ones of these differences are the ones that cause the disease? Because we can see, oh, this looks like it's a mutation in a really important protein, and that protein also happens to be related to whatever disease you have. So those are the kind of questions that we're actually building a really huge database of what's called annotations, which is basically those kinds of, when people have compiled a ton of different data files of this mutation means this, or this mutation could have this effect. And so we're in the process now of compiling a huge database of tons of those annotations so we can answer those questions and help clinicians answer those questions more easily.
What does your parallelization architecture look like?
So it's not that much, it's not that interesting computationally, it's more interesting biologically. But basically, so your DNA is split up into these uneven chunks called chromosomes. And if you cut a chromosome in half, and then try and just like do all of this stuff for half of a chromosome, then you run into problems on the edges because it depends on things that are like on the other side of where you cut. So things don't happen correctly, those edges, if you cut them. So what we do is when we cut things, we actually cut, like we do an overlap, so you like cut a little bit too far one way and a little bit too far the other way, so like your cuts overlap. And then we've got algorithms that say, okay, now that we've got all of these overlapping pieces, we've got the pieces that we did and the overlapping pieces where it could actually matter that we cut things, how can we put them back together and actually extract the data that we would have gotten if we hadn't cut it in the first place? So, and that's actually pretty important because some of the shortcuts that a lot of people use to do this stuff is, say you've got, you sequenced a whole bunch of DNA, and some like little pieces of DNA, you happen to get a whole bunch of chunks for that little piece, and so you just kind of like throw away some so you don't have as many pieces to work with so that you can do things faster. But that ends up bad because usually it's just some random selection you throw away, and if you run it again, it might throw a different random selection of pieces away, and then your results aren't the same from one to another. So when you can parallelize it like this, you can use all the data you have every time, and then you get the same exact result every time you run it. Which is important.
I'm trying to figure out how to ask this question. Is there any order to the functions in the genome? Like, is there a certain chromosome that contains like liver cell production, or is it just randomly distributed? Does that make sense?
Yeah, and it's like there are big chunks that that we know do certain things, but it is fairly randomly distributed. Obviously, so X and Y, those are probably ones a lot of people have heard of with the sex chromosomes. Those obviously have important things to do with whether you're a male or female or things like that. So there are things that we definitely know, like, this chromosome has a lot to do with this particular thing, but it is a lot of just kind of spread out. I actually saw a picture once of like all of your chromosomes, and then it was like, and then it was like pointed at a body of like a picture of a human body. We know this part of this chromosome controls this part, and it was a whole big mess, but pretty cool to look at. So yeah, there's some more to it, but it is kind of random. How much, I mean, it's been optimized for how many billion years, how much of it is actually random, but yeah.
Well, let's thank Garrett for showing us the source code. People don't have numbers on their tags, I think. So we got to figure out that before we do our drawing. What was the last number we got to? Like, who has 22? You can just check your tag real quick. You have 22? And do you have 23? 23? 25? Who has 26? Okay, raise your hand if you don't have anything on your tag. Oh, wow. Look at all these slackers.
That's right.
So go ahead. 25, 26. Okay. Oh, okay. So
Okay, 26.
26. You're 27.
27.
Who does not have it? Okay. 28. Do you have a pen here? I have a pen. And 29 is right next to you.
No.
And who else is blank? So 30, I think?
30, 31.
Okay. See, self-organization.
31, 32.
You'd be 33?
Almost. So what number are we on?
Didn't go through anybody's eye.
35. You have your 35.
Who else?
That's it.
Wait, Rocky, did you get a number?
Yeah.
Okay, so everybody's got one? What number did we get to?
35.
35 plus 1 since I'm 0. And let's import random. And random dot rand int. Nope. And 0 and numpythonistas. See how easy coding is? Okay, pair program. Can you guys review this real quick before I merge this? Sweet. Speaker, would you please press enter? 8. Who's number 8?
Oh.
Lucky number 8. Congrats. So our next talk will be time series, December 3rd, 6th, December 6th, January 3rd. That was the one that got me.
You can spell parquet though, so it's okay.
And it'll be right here. Yeah, thanks for swinging by. If you want to talk to me, that's awesome. Now's the best time to plan things. I'm going to be helping to clean up the space. Thank you for coming. Please drive home safely or get home safely.
Thanks.
No idea what you're talking about.
Yeah, that's kind of why I did it, because I know that it's hard to
Let me take a look.
like communicate this kind of stuff. I knew I needed to do it the first time sometime, and you guys had to be on a test subject, so I'm sorry.